Traditional laboratories have for centuries looked largely the same with waist height benches. And while these laboratories often have good space utilization, they usually lack vertical space utilization that is automation friendly. Now, what if a single robot arm could access 60 feet of bench space without moving an inch? To do this, we'd flip the script. In a vertical lab, equipment would go to the operator rather than the operator always going to the equipment. So let's talk about three things in this talk. First is vertical automation. Second is additively manufactured alloys. And then third is advanced optimization. So first, let's go back into the vertical automation aspect. As an example, let's take some kind of inorganic solid-state synthesis procedure. We may need to do some powder dispensing. We'll have something where we're doing processing and synthesis. We'll characterize our materials and we'll do some kind of testing. Now, in the traditional laboratory, you have some of this equipment on benches and then others that are freestanding, standalone. And then one of the ideas we've seen is we put a robot on wheels and use a mobile manipulator. But in a vertical lab, we do something like a vertical lift module that can store and retrieve powered equipment. And by the way, VLMs, not to be confused with vision language models. This one did come first. So we have our equipment sitting on trays instead. We have some kind of operation bay or table. We have storage in the front, storage in the back, and an elevator or lift in between. So we can take this equipment and move it up to a storage position, and when we need to swap out a sample or perform maintenance tasks, we bring it back to the picking position. Now let's take a short ride on one of these vertical lift modules. So we see the tray entering the lift, sort of elevator. And then we'll kind of take a ride from the equipment's perspective here. So now we're going up near the ceiling. See a little bit of light coming through the roof of this, and we'll go back into, in this case, the front storage. And when we're ready to retrieve the tray, we follow tray 1 for pneumatic aspect. It's very straightforward. And bring this tray back to our operator bay. In a relatively small or medium-sized lab, we'll say about 300 square feet, adding one of these vertical lift modules could increase the footprint, at least the automation-friendly footprint, by about 50% or more. And vertical lift modules increase automation-friendly linear desk space compared to alternatives. So let's take an example with a fixed robot. You have one robot, maybe on a pedestal, and then you surround it with equipment. In the traditional sense, you clear a path for a mobile manipulator to navigate the space, and in kind of maybe a slightly more flexible or a easier to spin up configuration, you have a rail and your robot arm goes along this rail. Now, a vertical lift module can fit a lot of equipment and consumables. So here I show what could fit in an example configuration, and that's not to say you should put this exact configuration or all of these parts, but these are fairly common in the self-driving lab space, different tools. So 8 of these Opentrons OT2 liquid handlers, 3 of these large CNCs that people often put kind of custom tools on, 12 of these smaller ones, hundreds of weld plates, thousands of vials, tens of thousands of pipette tips, and then a little bit of extra space for whatever you'd like. So this is where a single robot arm could more or less access 100 linear feet of. If you were to take this and kind of stack all of these modules side by side, it would be around 100 linear feet of desk space required. Now, in 2023, I ran a feasibility study for adding vertical lift modules to the Acceleration Consortium's new building that has a January 2027 launch date, so in about 13 months. And this would cost about $240,000 per floor, 3 floors. 2 of these would have the powered tray options, and then 1 would be just for more kind of boring dry storage for things. And this was unfortunately shelved because of vibration concerns. When I was doing vibration testing during the feasibility study, it just wasn't something that we thought sensitive equipment could be placed on. Now, 6 months ago, I revisited this and I learned that some vendors had belt-driven rather than chain-driven systems, and these had significantly lower vibrations, and the tests were really promising. Now, unfortunately, there were some equipment delays, procurement, electrical certifications, all of that, and with my transition to Brigham Young University as an assistant professor, I was kind of running out of time. But I didn't want to get discouraged. I still wanted to make a showing for finding some kind of middle path with a lab in Mississauga that I've managed over the last couple of years. And while this lab, the AC Dev Lab, rebranded from the AC Training Lab, while this has supported several visiting researchers during these extended research stays, they've come in, learned about AI and automation in the context of research projects that they proposed and carried out here, PhD researchers in this case. It remained mostly empty during the other times because it was really hard to get to from where I ended up living in Ontario. 3 weeks ago, we moved all the remaining equipment that had been in Toronto and nearby to this lab. And we added sliding shelves to enhance the horizontal and the vertical space utilization, and a 10-foot horizontal rail and a 3-foot lift that increased the robot arm reach, generously loaned on short notice from some of the other labs. So we can take a look here. We have kind of from the side view, the arm being lifted about 3 feet on this lift module, not a vertical lift module, but just sort of a telescoping lift like you'd find on a desk. And then we have this situated on a rail, so we can bring this back and forth about 10 feet to really increase the space. Now, in this early prototype, it's pretty wobbly, and we are definitely we already have some measures in place to address that. But quick, rapid prototyping, proof of concepts are important here. And a gripper camera, with these sliding shelves and with a lot of reconfiguration, I'm very, very much a fan of flexible automation and doing so in a way that is truly modular, truly flexible. One of the ways we can do that is to use these fiducial markers, what are called fiducial tags, called April tags, and this can help you with orienting yourself from the global reference frame into a local reference frame. So if you have a rigid object and you put one of these tags on here, sort of like you can find the origin of this rigid system, like a liquid handler or a powder dispenser, even if that's moving on a shelf, for example, or you happen to tilt it by 2 degrees or shift it by 3 millimeters. And so this is one of the things we have here. Daniel New is a CS undergrad at U of T, and he's also applying to grad school. So if you'd be interested in him reaching out, I'm happy to connect you. We also used an auto retracting cable to provide flexible power. You need to have power go along the rail. More traditionally, you'd use cable carriers. This was a solution that was working okay for us in this case. And it became really important when we were doing this very space efficient planning, especially as we started looking at vertical planning to do some rough CAD modeling for things. So this wasn't a perfect digital twin representation. We weren't embedding a lot, but it really helped with space planning to take a look at the side and see the reach of the robot arm relative to these shelves, and make sure that certain pieces of equipment could fit on different shelves as well. And so this really helped out with layout planning. Now I'll show you a time lapse of the last few weeks, at least quite a few chunks of that, and hope you'll enjoy this for a moment. So here you can see the sliding shelves moving back and forth, back and forth. And over several days, we're kind of organizing and sorting and bringing things together on these shelves. Now we got the linear rail in, and we began setting that up. We got kind of a second round of shipments from Toronto, the rest of the equipment, and we started building things around this linear rail with the robot arm. And it happened to get left off at this, but it was. I think this is kind of true. I certainly had some sweat on my brow from this, as well as the other people that were helping me here. Now I'd like to take you through a brief sort of flyby walkthrough of this AC Dev Lab. So on the left, we have an optical microscope, and on the right, a electron microscope, a desktop version of one of these. We have some Opentron's liquid handlers, a Flex, an OT2. We have in the back right a Mettler Toledo powder dispensing module, some different resin printers, one that can do auto releases off of the build plate. We have some leftover electrochemical experiments from one of the visiting researchers, where we did custom 3D printed electrochemical cells. This is another one of the resin 3D printers. We have some lower cost powder dispensers that are still fairly accurate. We have this liquid color matching machine with the camera that's live streaming to YouTube 24/7. Another station where somebody was doing viscosity optimization for kind of towards battery slurries. And then here we have the 10-foot rail, the arm, and the lift. And so if we go in a little bit and take a look from the side, we see up there we have that gripper camera. We have the lift going up by 3 feet. Lots of single board computers around. We have the flexible power on the side, and then we have a calibration board for the camera. It's a one-time calibration, and then these April tags you can see on the right, these sort of QR code like tags there. We're still doing some rearrangement in the lab, but we had a 3D printer and then these sliding shelves as well. And one of the key aspects of the sliding shelves here is not just the space utilization, but the ability to have a person go in and access the sides without crossing the rail. And so anytime you install a rail in a lab, generally it's no longer a cobot friendly workflow. You have to sort of section that off as due to safety concerns. And so that's one of the things that with the vertical lift module kind of comes embedded in it, is this ability to have sort of safe cobot friendly workflows. This was a kind of a middle path to get the same sort of thing in this lab. So that's the AC Dev Lab as of last Friday on Saturday morning. Let's now shift gears a little bit and talk about the materials application here. So we talked about vertical automation. Let's talk about additively manufactured alloys for aerospace applications. So metal 3D printing, this is something that, as a good case study, it enabled NASA to have these rapid feedback cycles and reduce the processing complexity for a particular part on this rocket engine from 127 welds to only 4 welds. And so this was a rather complex geometry, and if you imagine having 127 welds for this one part, that can be a pretty lengthy and time-consuming process and be rather difficult. In this case, we had one of these parts that flew on these kind of static fire tests as well, and so kind of a really important success story for metal 3D printing and how increase the speed with which they were developing these different tools and parts. Now, ultrasonic atomization is a technique that we can use to enable chemical white space discovery for additively manufactured alloys. And what I mean by that is you can have elemental powders and master alloys that are kind of preformed compositions of alloys, and you can homogenize these with an induction crucible. A crucible that's heated with inductive coils, and then apply a pressure gradient to, once it's homogenized, to drip the molten metal onto an ultrasonic plate. They call it a sonotrode. And in doing this, you're able to actually get these powders to, these droplets to spherize. And so that's the ultrasonic atomization part of it, is making highly spherical powders from this kind of molten alloy dripping onto an ultrasonic plate. So here's an example of that. You can see the molten droplets going onto this plate, and then the spherical, the powders going off and then being collected in a chamber elsewhere. This is an example of ultrasonically atomized aluminum alloy powder. So you can see this; it has pretty good flowability. That's one of the features that we're looking for, and it has good sphericity, good particle size distributions that are amenable to 3D printing these alloys. And laser powder bed fusion is one type of metal 3D printing that can come in a desktop size. So if we take a look at one of the pucks for this, you'd be printing on a build plate like this that's screwed in. So this is good for kind of lower volume research. And take a look at the laser powder bed fusion processing.
We can help you out with like printing.
You can see the laser rastering the patterns on this thin bed of powder, and then you kind of sweep something to deposit a new layer of powder, and then continue with your next layer of the print. So here's an example of, on a much larger build plate, but an example of a metal 3D print. You can see these complex geometries that normally would be very difficult to get with, or impossible to get with traditional manufacturing methods. So a vertical cloud lab, tying back to the vertical automation aspect, would facilitate powder mixing, processing, synthesis, characterization, and mechanical testing using, for example, an array of different types of powder dosing equipment on the trays, some desktop synthesis and characterization modules, and then the things that need to be freestanding that are much larger, those are placed to the side, starting out with sort of human in the loop transfer of samples, and then potentially bridging into some more automated sample transfer workflows here. So we talked about vertical automation with vertical lift modules and automation-friendly space utilization. We talked a little bit about additively manufactured alloys as one of the kind of key research thrusts I'll be having at Brigham Young University going forward. And now I want to talk a little bit about the AI side of things, the advanced optimization that comes into play in performing this materials discovery task of better, stronger aerospace alloys. As a brief primer on Bayesian optimization, here we have a surrogate model that predicts properties and quantifies the uncertainty of those predicted properties. Along the vertical axis, we have f of x, our objective function that in this case we're trying to maximize. Along the horizontal axis, we have our one parameter x that we're tuning. And in black dots, we have our noisy observations, our existing data we've already collected. In blue, we have our surrogate model, our predicted properties, and in the bands, the predicted uncertainty of those properties. And unbeknownst to the model, in the gray dotted lines, we have the true model, unbeknownst to the algorithm, we have our true underlying model and the star as the global optimum. And we have something called an acquisition function that guides how to select the next experiment. On the bottom plot, we're plotting a common acquisition function called expected improvement as a function of the same single parameter x. And when we plot that, we can see that the maximum of this function, the red dot, is at around 3.85. Now, this is what the Bayesian optimization algorithm is suggesting as the next best experiment to run. And we do this in a loop where we add that data back in, we refit the model, and we continue this in an in an optimization loop, slowly converging on our optimal solution in a very data efficient manner. And this is what would typically be referred to as vanilla optimization. So let's start out. Real world materials discovery tasks, such as alloy design, require more than just our vanilla optimization. So we will often have multiple tasks, so-called multitask optimization with simulations and different fidelities of experiments. We have always multiple objectives that often have competing trade-offs with each other, so they're competing objectives. We have a mix of continuous and categorical variables. We have these compositional linear constraints, that the sum of everything has to equal 1 or some total. These are often high dimensional. Here you can see an alloy data set that covers kind of a large database of aluminum alloys. And there are 23 or so unique periodic elements represented in that database. Now, not all of those are represented at the same time. You can't really have this 23 element alloy, and so you end up with these n choose k nonlinear constraints as well, and dealing with those can be a bit tricky, a bit challenging. You will likely not have more than maybe 6, 7, 8 unique periodic elements within the single alloy. So we take all of these and we say, okay, we have single versus multitask, single versus multi-objective. For each of these. On the far left, this is what we would call vanilla, or this basic optimization strategy. Now, changing it to, say, multi-objective and high-dimensional, now we're saying this is an advanced optimization task. And there's a tool called Honigumi, I'm very proud of, over the last few years, that allows you to dynamically generate minimal working examples for these advanced Bayesian optimization tasks. So in the basic vanilla BO example on the left, we have something that's maybe about 20 lines. When we toggle to multi-objective and high dimensional, we are changing some of the way that we're interacting with the package. It triples the number of lines required in some cases. So looking at this is something that can pair really well with large language models. You can think of this as sort of a templated code that you can base things off of. So we have Honigumi, this interface for accelerating the adoption of Bayesian optimization in the experimental sciences. Major thanks to Andrew Falkowski and Taylor Sparks for their work on this as well. So I'll show you a quick demo of the Honigumi website, which is really where the heart and core of the tool is. It's not a wrapper. It's not a Bayesian optimization wrapper. Think of it as sort of like a complex Bayesian optimization tutorial generator that's self-consistent and fully runnable. So if we take a look at the web page, we scroll down a little bit, we'll see this grid selection, similar to what you saw in the previous slides. And this would be the vanilla Bayesian optimization, everything to the left. And if we just get kind of obnoxious and turn everything to the right, the more advanced task, we can see this script dynamically populating and creating self-consistent, kind of self-contained script with all of these. Now, part of the great piece with Honigumi are the tutorials. And so these have 6 material science focused tutorials. So for example, doing multitask optimization across different ceramic binder systems. And it shows you how to, kind of sets up the problem, shows you how to use Honigumi, and then how to modify the template and kind of address the problem statement. Now, it goes beyond that and has some conceptual documentation. So if you want to learn about some of these concepts like single versus multi-objective, or frequentist versus fully Bayesian, I mean, like kind of better with high dimensionality. You can learn about some of the math and concepts there as well. So we talked about vertical automation with vertical lift modules, kind of rethinking the way we approach automation. The operator doesn't always have to go to the equipment. You can actually have the equipment go to the operator in some cases. Additively manufactured alloys are a self-driving lab that can be rather difficult to automate, but very impactful for these aerospace applications, like with NASA and other types of structural components. And this is the one of the key focuses I'll have at Brigham Young University in the coming years. And then we talked a little bit about advanced optimization in the context of alloy design and how we can leverage a tool called Honigumi to quickly create our Bayesian optimization scripts to perform this optimization. So in summary, while some might say the future of science is self-driving, I would add to that, I think the future of self-driving science is vertical.